I'm going to be talking about the contributions from GoldSpot. I myself am one of the, I guess, geology/data scientists at GoldSpot, and there's a small group of us at this company, which is kind of a services provider that works with data analytics and data processing, assisting some of the transects for Metal Earth. So we've been assisting, like I said, with a variety of tasks, roughly kind of housed under the data analytics banner. And most of these have related to things loosely related to geophysics processing. And these have been in direct correspondence with individuals. So for example, looking to improve, maybe or reduce some of the artifacts in the seismic sections, or integrating different data layers together, but not directly contributing to a product ourselves, rather providing some support. However, we've also been looking at ways of integrating data layers in situations that can assist regional mapping. And this is intended as a collaborative exercise alongside the transect leaders. So most recently, we've been working with Kate at Larder, and previous to that in the Swayze area. So in this vein, we have one publication accepted in late 2020, and that relates to use of deep learning for automated detections of fault in geophysics. And we have 2 articles which are being written now, which relate to remote predictive mapping of bedrock for the Swayze and the Larder areas. Before I get started, I'm just going to clarify that when I use the term artificial intelligence, what I mean is automation techniques that mimic what could be done by a human, but is instead done by a computer. So I would expect you're pretty well familiar with that from Leo Feltrin and his students and Rebecca, but it's always worth saying because sometimes there's some lack of clarity around these terms. So a subfield of artificial intelligence is machine learning and deep learning. And what those really are just families of algorithms that use different approaches, mathematical approaches, to find patterns within data layers or within stacks of data layers. The important point to make is that these machine learning techniques or data analytics techniques are like any mathematics or statistics at all, and that any garbage input is going to lead to garbage output. So it's critical that geoscientists are involved at basically every single step of the way, from selection of the data layers, pre-processing of those, selection of the algorithm, and then validating the results. So it's always important to say that this is not some kind of approach which is meant to replace the geologist. What it rather is a tool that supports geologists. So this brings me to the idea of machine-assisted mapping or remote predictive mapping. Effectively, what happens with machine-assisted mapping is that we take areas of known mapping, say from the government survey. We train an algorithm to recognize a pattern in geophysics or geochemistry, which is associated with every rock type. And then we use that newly created machine learning model to classify rocks under cover or under lakes, or even to reclassify areas which have already been mapped. And you'll see a kind of trend in the way that this is done. We start with some training information. So this could be an outcrop map, it could be an existing GIS map, it could be a paper map which is brought over into some kind of digitized form. There's a stage where we create this machine learning model, and it's really just a statistical model trained to recognize patterns in a data stack that relates to some known information, being the bedrock mapping. And then when we present new data to that model, it is able to make a guess at what those new data pixels might represent. So that's the classification step, and the result in our case is a map. And the reason why we do this is because although we could use a conventional technique like a light table and many stacks of paper, this is intended to add some level of, I guess, objectivity and reproducibility to bedrock mapping based on multiple layers, and also to provide a way for multiple geoscientists to look at a product and sort of assess that and work together to make an improved version. That is potentially like a little bit of an abstract arm-wavy way to describe it. So I've got this little animation which helps to bring it maybe make it a little bit more clear. So again, we're taking areas with maybe known mapping and a stack of information like various derived geophysics layers from magnetics and gravity. Sometimes we use things like topography or remote sensing, hyperspectral information. And effectively, you're sucking out the pixels from that data stack, which are now attributed with multiple layers of information, and they're poured through your classification algorithm, and out the bottom comes some assignment of a class, of a rock type. And this is really based around the fundamental work done by Jeff Harris and Eric Grensky years ago, and is now essentially a pretty well-established approach. Moving on to the Larder area, at the end of the day, machine learning stuff is often not very difficult, but it's the data processing and the data organization which are absolute murder. But once the data are gathered, QA/QC'd, and sort of stamped for use, then we start to produce derived information from those data layers. So for example, we might start with a TMI magnetic image, which is reduced to pole to place the anomalies over the bedrock type. And then we can use even further processing to create things like the first vertical derivative or the tilt and the short and long wavelength, pseudogravity, things like this. So this has been done for both the Larder and the Swayze areas. It doesn't really capture the amount of time it takes to do this in a single table, but there's a fair amount of elbow grease involved with that step. At Larder, once we were able to look at the data available and the resolution of the data, it was quite clear that we should start the process in a smallish focused area. And this is at the north of Jackson's 1995 map in an area we call the ARM 50 block. And this is just a series of higher resolution mapping areas that correspond to geophysics. This is a close-up of the ARM 50 region, and it shows some of the extracted data from the RTP magnetics. And this is an example of some of the layers which were fed into the machine-assisted mapping workflow. So you can see, for example, where the value starts to come out of this process, that in the existing 1 to 50,000 scale mapping and in the government mapping, we don't see quite as much information as we can extract from the processed geophysics data. So it's clear that there's quite a lot more small scale stratigraphic units, and that there's a lot more folding that has been previously mapped. So we're looking to leverage this extracted information to produce better maps. And again, coming back to the idea that why would you use machine learning mapping rather than just getting a pencil out and starting to draw? I think we can look at that in terms of how much data a person can look at a given time. So for example, if we take that data stack of ARM 50 geophysics and we start to plot one layer against another on bivariate plots, this gives us the ability to look at 2 layers at a time, but all the layers in aggregate. And you can see that there are some trends in these data, but it's not strictly obvious how they might relate to different rock types. So that's kind of looking at things 2 layers at a time. We could also take 3 layers, and we could create a red, green, blue ternary image where each of those color channels is represented by a different data layer. So now we're looking at 3 layers of information at a time, and we can see that there are some trends, spatial trends in the data of hot and cold colors. But again, it doesn't give us necessarily the discrimination we want to make a robust bedrock map. So here's where the machine learning adds the value, is that by combining many geophysics layers or remote sensing layers and extracting that information to be examined by an algorithm, we're able to essentially do what I just showed on the past slide, but in an automated way. And this is the result of that bedrock map over the Larder area. So you can see that it's slightly low resolution. That's because it's the test case draft, but that there are good consistencies with the existing map. We can see that things are not looking like a confetti or a shotgun blast. There's spatial continuity to the various rock units. And that, as a geologist, gives us the confidence that the predictions are likely to be accurate, because we would expect to see rock units adjacent to one another being similar. So you can see that the pixels overlain by cover in lakes are now assigned a rock type, and that these, as I was saying, these assignments are spatially coincident with observed areas that have been mapped from outcrop. So this is kind of the first pass stage of this exercise, where now we revisit the map alongside Kate and start to build in more validation layers. So we have kind of our first draft of this map. It's a bit rough. And now what are ways that we can assess this? So there's new observations that have been made from the field during the field seasons. And we also have legacy geochemical data. This work is ongoing. It's been challenging to gather and verify the geochemical information because it's often hasn't been compiled in a robust way by the survey, but we're slowly pulling together a database of this information, cleaning it and getting it into a form which it can be used to complement the machine learning maps. So the next stage would be, for example, to look at the lake sediment trace elements and whether or not we can validate some of the machine predicted rock units with geochemistry. So that's work that's going to be done with Kate and Hai Ming. And we'll also be doing good old-fashioned manual interpretation because, as you would expect, if we're using existing mapping as the precursor for the prediction, we are losing kind of some novelty of new observation. So by doing kind of conventional geophysics line work, we're starting to see faults, folds, axial trends that weren't captured in pre-existing mapping, and that will be progressively integrated into like a new baseline map, which then becomes the foundation of training for version 2. So you can see that there's kind of like an iterative looping of this process where we produce something that's a little bit better and we train again, we predict, we make something that's a little bit better again, and it kind of goes like that. So this is not a case that we just produce the best map ever in one shot. It's really a process of old and new techniques complementing one another. Okay, now I'm going to change tack a little bit, and I'm going to talk about another application of machine learning to regional mapping, and this relates to the interpretation of faults using geophysics data. This section is taken from the paper which is now in press with Computers in Geoscience, and in this section I'm going to move a little bit from what the workflow looks like and the reason for the problem statement into a little bit of background, but not too deep, and then the results for the Swayze area. So if you're familiar with geophysical image processing, you know that there's zillions of filters around, and every geophysicist and geologist has a few of their own favorites. One major subgroup of geophysical filters and image filters is called edge detectors. As you can imagine, edge detection algorithms are for finding edges. And I would say that this is very attractive to geologists or geophysicists because in for example, a geophysics map of gravity or magnetics, an edge is often the juxtaposition of two contrasting petrophysical properties, so like two different rock types, or maybe a large fault or something like this. So the traditional way to find edges in geophysical maps is to look for strong gradients and then to use moving window filters and things like this to find a way to assign a line to what is effectively a steep gradient. This is very useful because where the lines are continuous, we might infer a rock type. If we see regions where a number of lineaments are ending, that might be a spot where we can infer a fault. The caveat is that because imagery is very variable and the response in the geophysics layers is also very variable, the edge detector algorithms often don't work perfectly in every geological situation. And they also require a lot of artful fiddling, which is okay, but that level of subjectivity means that the results vary quite a bit between users. So at this point, the question was asked by my colleague, Amin, who's a data scientist. what if we could use something from the deep learning toolbox from image analytics to recognize patterns in geophysics data and in this way predict faults? And the reason why deep learning is attractive is it's a very active and robust field for things like, Google Image Analytics and Facebook. All these types of companies are releasing their code to the public. And we now have the advantage in the geology world that we can kind of borrow from those other disciplines and apply it to things like geophysics information rather than cat pictures. So the workflow consists of 4 main steps. The first is data preparation, very important because we need to think as geologists or geophysicists what data layers are likely to capture the signal of faults or the signal of rock types. We need to then choose an appropriate deep learning algorithm. In this case, it's convolutional neural networks. And we need to feed known fault locations in that have been digitized by experts. The predicting machine learning algorithm then produces some output, which is not necessarily useful on its own. So we use something called cluster analysis, which finds groupings in the prediction, and these groupings relate to being faults. And then finally, we add Linework, which produces something which is GIS worthy, and we can now use that as a geologist. Now, what Amin wanted to do in this case is use faults that were digitized by reliable experts that weren't from any of the metal earth areas as training information. And the reason for this is that there's always a risk in machine learning that you teach your algorithm something that it's going to see later on. So for example, if I took a big fault in the Swayze and I train the algorithm to recognize faults, and then I show it the Swayze once again, it will of course find that exact fault perfectly. But that's a spurious discovery. That's not a good prediction. So instead, what Amin did is he took information from the Quest area in British Columbia and from Australia in New South Wales. And you can see here an example of what the geophysics data stack looks like, and you can see the digitized faults here. This is just a close-up of the kinds of image patches that the algorithm is fed, because we break those images up into little tiny squares. And this is an example of the digitized line work from experts. Now, it's a bit too thin to be used properly. It's just only a single pixel wide. So what we did is we applied a kind of Gaussian distribution about that line work so that we have the known fault and then kind of maybe the fault is there on either side of it. And that's because at the scale of government, regional mapping, is the line really right over the fault? Maybe, maybe not. Maybe it's a bit shifted. So we need to have a little bit of wiggle room there. Then the information is fed into the convolutional neural network. This is kind of an abstraction of what that looks like. All the little image patches are placed into the algorithm, and they're progressively abstracted over and over again using deconvolution until they are just kind of a mathematical formula that is then rolled out to the new unknown data. And the results look like this. So this is a probabilistic representation of fault locations using one of the training areas. And you can see, for example, in a place like this, there's a break in that fault where the probability kind of dies off, but in the original data, it's a solid line. So we're getting an indication here of where a human might have extended line work, just through a region, but where the geophysics signal doesn't complement that assumption. Then, using a clustering algorithm called dbScan, the probabilistic representation is grouped. So this is kind of a complicated looking diagram, but what it's showing is a little region of space with a search sphere or search window. And it's saying for any given pixel, it has a result of whether or not it's likely to be a fault. Is it in agreement with the other pixels around it? And if it is, then it's given a high probability. And if it's not, it's giving a corresponding low probability, which allows us to produce this, which is taking the 0 to 1 probability of fault to a 0 to 1 probability of fault in addition to, is this fault likely connected to something nearby it? So what we have here are little fault segments. And this is helping us to maybe infer truncations of faults that may just die off, or it might be that there are other undetected faults that they truncate against. This is the way that the Linework looks when we skeletonize the cluster results into polylines. And then what Amin has done is produce curves to give something with a bit more of a geological feel. Now, obviously, we don't have faults that bend around 90 degrees at an elbow, and we don't have kind of wiggles like this. But what this mainly is a proof of concept showing that the work can be done. And finally, we have the results at Swayze. This is, again, a proof of concept. The original digitized faults are shown here in this map. And then in yellow and black, we have the predicted faults over the region. And in the background, the blue map is essentially a heat map, which shows the lighter colors as high probability for containing faults, and the cool colors as areas that are unlikely to contain faults. And in this way, we can even create structural domains and sort of separate those and investigate them more closely. As I was saying, that paper was accepted for publication late last year. And what we also did is take the code for this and the trained model and place it all up on the software repository GitHub so that other people can take advantage of this work, manipulate it, amend it, and what have you. Because as I was showing here, there isn't a fantastic, it's not a 100% perfect representation of the faults in the area. Although, speaking with Raz, there are probably areas which have predicted faults which are previously unrecognized due to cover. But I think that this can be improved with more geological love and a few extra training areas, but that will be work for the next generation of researchers. So that software code is available. So just to wrap up, what I was showing today is kind of related to the theme of regional mapping and ways that we can take stacked data information, integrate it together, and produce a result which hopefully will support regional interpretation. The next steps in the Swayze and Larder bedrock prediction world are to gather the geochemical data and use that to validate results, but effectively all the code and workflow is finished. We've also looked to take that workflow and rebuild it using only free software like QGIS and a machine learning platform called Orange, so that we can teach the transect leaders how this work is done, and then it can be kind of something that they can do autonomously. Something I didn't talk about is the work that is upcoming, which relates to the seismic MT and the passive seismic and the MT interpretations, which is really just integrating those 2.5D and 2D work into the 3D models. And in this way, kind of extend some of the bedrock interpretations into the third dimension. And that is it.
Thank you very much, Shawn. Appreciate the presentation. Is there any questions from the live audience?
I've got a question for Mark.
Okay.
Can we turn it around? I was wondering, Mark, you mentioned remote predictive mapping as some of the foundation for the work that you showed. And I was very curious to know if any of that has entered the public domain, because it would be really interesting to compare what is kind of the established workflow for bedrock mapping on land to any innovations that you might be seeing from the undersea world.
I'd love to say that we have a very sophisticated and even automated workflow, but the fact of the matter is we're still doing it the old-fashioned way. And we'd love to get involved with what you guys are doing to kind of improve the resolution of what we do and the integrity of what we do. So I'll be talking to you.
Great.
Hey, Shawn, there's Rebecca put in the chat here. Why did you pick DB scan over another clustering technique, and what transformation did you use for the clustering?
Which search distance, Rebecca? like Euclidean versus anything else?
No, more so all the underlying assumptions with dbScan are different from any other clustering technique like k-means, fuzzy c-means, and so on. Why did you pick dbScan for this application?
Yeah, okay, so the reason we didn't choose any of the more conventional ones like, say, like k-means is because there's an assumption of Gaussian distribution, of course, which is like never satisfied ever in geology. And HDBScan is a lot more robust to that. As well, it gives us the capacity for fuzzy clustering, which is very important, I think, in geology situations, because you don't want a single result. You really do want that kind of flex and wiggle where the expert then looks at things and goes, well, yeah, that's not right. Or, you know, I see a very faint shadow over here and that should be a rock type, but it's just not expressed in the geophysics data very well. So the other option, you know, for fuzzy clustering might be fuzzy c-means, but fuzzy c-means has a few Gaussian assumptions as well. And so I don't like it.
All right. Yeah. And for transformation, what transformations were you applying?
That's a good question. This work is you know, comes from a mean, and I was only the second last co-author, and so I would have to look again, but I can send you the preprint. And yeah, no, I can't recall from when I worked on the paper. Sorry.
All right, thanks.
I have a quick question for you, Shawn. So do you guys have a workflow to deal with shear zones? Because many of these fault lines on a map are actually volumes in reality and broader shear zones. So have you thought about, have you guys considered ways to integrate that fabric analysis or something into your?
Yeah, definitely. That's a good question, Ben, because there's two schools of thought in the machine assisted mapping world. One is that you should look at the data independent of space. So essentially when you suck out the pixels, they're placed into a giant matrix and you don't look at the XY location at all. It's purely on the basis of merit of pattern comparison. And that's what I've done here. I like this approach for the first stage because there's no assumption that just because something is close by, you should call it something else. However, of course, if you think about the problem for more than about 10 minutes, you know, you realize, okay, well, this is the whole reason we have, you know, spatial statistics. And this is why, you know, you would use kriging or something like this, as is typical in the more old fashioned ways of doing it, that you're looking for that continuity, for example, along a shear zone. So the second stage of this process, like once we do this rough first pass, and we sit down with Kate and we build in all the field observations and things like this, what we'll probably do is create a weighted prediction matrix, which is effectively, we'll probably use a version of kriging called Gaussian process regression. And that essentially is looking for spatial continuity on a local level. And then you have another matrix, which is the clustering, and you multiply those two together so that you get the various little clusters, but also then they're augmented because they're either along strike from one another, or if they're off strike, they're decreased. I don't know if this is answering your question. It's kind of getting around the specific issue of the shear zone. So I think this puts me at odds with a lot of other machine learning geoscientists. I think that it's better to make the distinction of whether something is a shear zone or a brittle fault or what have you, based on your expertise as a geologist, and assign that manually, because the amount of work it would take to do it automatically is not worth the time to just use your own expertise. Maybe, but others would say yes, but if you can't render this to like a kind of semantic mathematics problem, then you're a giant failure. So it's like an 80-20 thing.
Yeah, it's a hard problem. So that's
no, it's good. I'd be interested to chat with you a little bit more about it. And if you have some specific case study areas, maybe we can use those as like a bit of a toy to improve the process.
Cool. Thank you.
All right, I
Shawn,
think-
I want to follow with the same that Richard asked. You use for your lineament detection, ejection, 6 products of the magnetic field. Looks like, doesn't that look like be redundant if you included some independent data set, let's say EM survey or something like that, how that would affect the final results of those fault detections rather than using, like, I would say a machine that is smart enough should know that all 60 products are derived from a single data set.
Yeah, so Pejman can probably jump in. I see he's online, but my thought on that is that if we were using traditional, like quote unquote, old-fashioned machine learning, like say random forests, that the conditional independence of the layers is very important, and that's why you would use principal component analysis or something to have each layer rendered into the most different signal as possible. And then you could even manually throw out, you know, noise and things like this. In a convolutional neural network, however, because of the way that it is abstracting the data, I believe that function effectively is made internally. So like in the first layer or two of the CNN, it's effectively building image filters, you know, like edge detection and things like this. So it's going to see some patterns across different layers. Like for example, the tilt short wavelength is going to look a little bit like the first vertical derivative, and therefore it's going to see that signal twice, and therefore its edge detection filter layer is going to be a little stronger for that particular feature. But is that bad? Because as a geologist, I would also use those two layers in a complementary way to see that, oh yes, this thing is striking and then it ends. But then in the tilt derivative, you get that impression of 3D-ness where you can see the things dipping off. So I don't know. I'm unable to find the answer to your question in the literature so far because it's not a very active field, the machine learning bedrock mapping. There's really only about 15 or 20 people working on it, and most of them coming from Iran, interestingly. So yeah, it would be interesting to compare maybe two different feature input layers. One, say PCA, so that you know they're very different, and one, the raw data, and see how the results compare.
Thanks. That's
Okay,
good.
thanks. Before we'll have one more question. Eric, you got a question, then we'll cut it off after that.
Thanks for the presentation, Shawn. I was really impressed with what you've done with the structure. That's really good. Well, one question I have is, have you compared other methods? You've used neural networks, but have you compared things like random forests, or as you say, the more traditional methods, and looked at the results and how different they are?
No, we haven't. And because, I mean, as you know, I'm kind of like a random forests aficionado, maybe to the bad way, but, you know, Eric is bringing up a really good point, because often in machine learning world, we don't have true big data. And so a technique like random forests, which uses a bootstrapping selection, is more statistically robust to smaller data sets like we have in geology. I guess the reason why the deep learning was used in this case is because Amin was interested to try to resolve this structural geology problem into an image problem and then see how it would work. Whereas with the random forests approach, it would be resolved into like a more like a pixel problem rather than the entire image, you know, considered as spatially, like it wouldn't include the spatial distribution, I guess, of the pixels.
Mm-hmm. Yeah.
But it's a good point. Yeah, there's a few other techniques that we could probably use as well.
Right. Okay. Thank you.
Okay. Thanks, Shawn. There is a couple of questions there in the chat room for you, and we appreciate your presentation today.